Okay, hi, I'm Kyle O'Neill, and this is my presentation on resting, local, and action potentials. Alright, to start, in order to have an electrical potential, there must be a difference in overall charge between the extracellular fluid, which is here, and the intracellular fluid, which is here. In the extracellular fluid, there are positively charged sodium ions, which I have dog food for, and then in the intracellular fluid, there is positively charged potassium ions. The potential arises from the cellular proteins, which I have as the noodles here, which have a negative charge, which in turn makes the extracellular fluid more positively charged than the intracellular fluid. The extracellular fluid, or ECF, also gets a more positive charge because potassium is more permeable through the plasma membrane, and they sometimes just freely go up there and make it more positively charged. And then the reason that the ions are in the concentrations that they are is because of sodium-potassium pumps, which use ATP to pump sodium into the intracellular fluid and potassium into the extracellular fluid. The difference that is created by this is known as the resting membrane potential. The resting membrane potential describes the actual value of electrical potential of the plasma membrane when it is at rest and ready to send a signal down its length. The ICF's measured value in this state is negative 70 millivolts, which means the membrane is in a polarized state. Next, we will talk about the local potential, which I have this here for, the sodium channel. The local potential is a short range channel, or a short range change in voltage along the plasma membrane. When a dendrite is stimulated, a neuron's sodium gates open and sodium ions go from the ECF to the ICF. This disrupts the negative 70 millivolts, which is the resting potential, in a positive direction, and the plasma membrane is in turn depolarized. Local potentials are decremental, meaning they get weaker the further they are from the stimulus, and they are also graded, meaning the amount of sodium that passes through the channel depends on the strength of the stimulus. Once the stimulus is gone, the local potential is reversed, and the plasma membrane returns to its resting potential. Next, if a local potential is strong enough at the axon hillock, a more dramatic change in the state of the plasma membrane can occur. This is called the action potential. This occurs when the local potential depolarizes to the threshold and its value is negative 55 millivolts. Once this occurs, the sodium gates once again open and sodium ions rapidly diffuse across the plasma membrane to the ICF, causing the membrane potential to rapidly depolarize from negative 55 millivolts to 0 millivolts and eventually to positive 35 millivolts. After this happens, the sodium gates close, so now that's closed, and the potassium gates now open, causing potassium ions to rapidly go across the channel, or across the plasma membrane from the ICF to the ECF. The membrane potential now rapidly repolarizes as the existing cations cause the membrane potential to become more negative, eventually returning to negative 70 millivolts. And once this happens, both the gates close, the sodium and the potassium gates, and the sodium-potassium pump comes back, and it just keeps the negative 70 millivolts or resting potential.